Okay, so in this video, I'll be going over implicit differentiation. So before we get started, let's consider an equation such as this, f of x equals 2x squared. So as we all know by now, if we were to take the derivative of that, we would have f prime of x would equal 4x. So what they usually don't explain at the start of Calc 1 is that there's actually a little hidden dx here. And the reason for that is just because this ends up just being 1. So dx simplifies down to 1, so you have 4x times 1, and 4x times 1 is just 4x. So since mathematicians are generally lazy, we don't bother writing the dx. However, in implicit differentiation, we're going to have to end up writing something like that out. So let's consider this equation now. So 2x to the third minus, I don't know, 3y squared equals 5. Let's say we want to take the derivative of this with respect to x. Well, first thing we would just take 2x cubed. We would take the derivative of that just like normal. So using the power rule, we would end up with 6x squared. Now it gets kind of weird when we try to take the derivative of 3y squared with respect to x, because there's a y in there and we're trying to do it with respect to x. It gets kind of weird, but the beginning of it's kind of the same. We're still going to apply the power rule just the same. So we're going to end up having a negative 6y, and now here's what ends up being kind of weird. We're going to end up having this dy dx here. The reason for that is because we're taking the derivative of y with respect to x. And so we can't actually end up simplifying this down because I don't know what dy dx is. It's just a term we have here now. So oftentimes you'll be asked to solve for this, and you'll have to do some fancy algebra sometimes to solve for it, but that's where this dy dx comes from. And then taking the derivative of a constant, in this case 5, is always going to result in 0. So this would be your final result of taking the derivative of this equation above. So they get a little trickier than this sometimes too, and sometimes you'll end up having to do the product rule or the chain rule or the quotient rule in them sometimes, and you'll still end up doing all that the same way. It's just if you end up taking the derivative of y with respect to x, and anywhere in there, you're going to end up with that dy dx. So I suppose I can kind of show you an example of that. So let's consider, I don't know, 3xy squared, sure. And let's take the derivative of that with respect to x. So we've got a product, right? So let's take the derivative of this first thing, this 3x, so we're going to end up with 3, and then we're going to just kind of multiply by the second part, y squared. And now we're going to have to add on, and we're going to keep the first part now. We're going to have 3x, and then we're going to take the derivative of the second part, so the y squared. So derivative of y squared is just going to be 2y, and then you're going to end up having that dy dx because you just took the derivative of y with respect to x. And now you can kind of clean this up a little bit. This first term is going to stay the same, but now we can multiply this 3 and the 2 over here because multiplication is commutative. So we're going to end up having 6xy dy dx. And that'd be your final answer here. So I think I'll call it for this video. Like I said, you can also end up doing the quotient rule or the chain rule. So, but it'll end up working out kind of the same way. You're going to have dy dx's floating around through your derivative. So there you go.